Okay, working through problem set 6 on the topic of matrices. What we're going to see here is that a lot of the past exam questions involve finding eigenvalues and eigenvectors of a matrix and then applying that to the two situations that we saw in class, either trying to understand surfaces in 2 or 3 dimensions or trying to find the solutions to systems of differential equations. I'm going to start off with question 1, which tackles the second of those, systems of differential equations. We're given an eigenvalue, given a matrix, and we're looking for the eigenvalues and eigenvectors of that matrix. Now, we do have a 3 by 3 matrix here, so what we're going to do is work slowly through the eigenvalue problem because we want to be able to catch any factors that might arise. We don't want to just jump right into the cubic equation. So starting with question 1. In this, we're given a matrix A is equal to, let's see, 3, 2, 2, 2, 2, 0, 2, 0, 4. So we want to find the eigenvalues and eigenvectors, that is, the vectors v and the scalars lambda that satisfy the usual eigenvector equation. So the way we're going to do that is by calculating the determinant of the matrix A minus lambda identity matrix. That is, I'm going to find the determinant of the matrix A with lambda subtracted from the diagonal. So I have 3 minus lambda, 2, 2, 2, 2 minus lambda, 0, 2, 0, 4 minus lambda. So let's jump into the calculation of the determinant, but again, we're going to be going kind of slowly here because I want to try and catch any factors that arise. So the first term will be 3 minus lambda times the determinant of this 2 by 2 matrix. So that will be 2 minus lambda times 4 minus lambda minus 0 . Next we're going to have 2 times the determinant of this 2 by 2 matrix made up of these two columns. So remember to change the sign on that second term, multiplied by 2 times 4 minus lambda minus 0 times 2. And the last term will be 2 times the determinant of this 2 by 2. So we've got plus 2 times 2 times 0 minus 2 times 2 minus lambda. Now if I just multiply that all out, I'm going to end up with a cubic, which is going to be a pain. On the other hand, if I take a careful look at this, I might spot something useful. So let's dig into this a little bit more. So before we start multiplying out that first term, let's keep all those factors there. 2 minus lambda, 4 minus lambda. Let's take a look at the next two terms. So we've got minus 4 times 4 minus lambda minus 4 times 2 minus lambda. Let's take a little closer look at those last two terms. You notice that they've got a common factor of minus 4. So if I take that out, I get 4 minus lambda plus 2 minus lambda, which is equals to minus 4 times 6 minus 2 lambda. So there's a common factor of 2 there. If I pull that outside, I get minus 4 times 2 is 8, 3 minus lambda. And that's what I was looking for. That factor of 3 minus lambda there also appears back up here. So there's a common factor of 3 minus lambda in this cubic expression, which allows me to factorize the whole thing. So let me write that out a little bit more explicitly. We've got 3 minus lambda times 2 minus lambda times 4 minus lambda. And we've just shown that the rest of those two terms here are just minus 8, 3 minus lambda. Once again, I've pointed out that there's a common factor of 3 minus lambda in these two terms, which allows me to write this as 3 minus lambda times 2 minus lambda, 4 minus lambda, minus 8. So let's factorize what's inside the square brackets there. We've got 8 minus 2 times minus lambda times 4, so that's going to be 6 lambda, plus lambda squared minus 8. So in fact, those 8's cancel. We get 3 minus lambda times lambda squared minus 6 lambda, which gives me 3 minus lambda. Take out the factor of lambda, lambda minus 6. So that gives me my three roots, because this thing has to be equals to 0. I've got something times something equals to 0, which means that at least one of those things has to be equals to 0. So lambda is equal to 0, lambda is equal to 3, or lambda is equal to 6. Those are my eigenvalues. Before we go any further, we should check that the trace of my original matrix is the same as the sum of my eigenvalues. So I have the sum of the eigenvalues. Here is 0 plus 3 plus 6, which is 9. Let's have a look back again at A. We see that the sum of the diagonal there is 3 plus 2 plus 4 is also equals to 9. So we found that the sum of the eigenvalues is equals to the trace of my matrix. That's just a little confidence builder there that we've got the right eigenvalues. Next thing we're asked to do here is to find the eigenvectors of this matrix. So let's work through that. Let's start with the eigenvalue, lambda is equal to 0. So I'm going to calculate the eigenvectors of this thing by substituting lambda is equal to 0 into my equation A minus lambda I vector times V equals to 0, and solving for V. In other words, I'm going to take my matrix A, subtract away 0 from the diagonal, so it's just my matrix A, and solve the corresponding set of linear equations. We set it up in our neat little form like this. We're trying to find 1's along the diagonal. So what I'm going to do here is I'm going to take row, this is row 1, row 2, and row 3. Let's take row 1 and subtract away row 2, just to give ourselves a slightly neater notation, a slightly neater form here. So taking row 1 and subtracting away row 2 gives us 1, 0, 2. Doesn't do anything to the right hand side, of course. Let's see what we can do about that second row. Well, I could take away row 2 minus row 3. To give me 0, 2 minus 0 is 2, 0 minus 4 is minus 4, and again I've got 0 on the right hand side. And let's leave row 3 as it is for now. Why don't we just make row 3 divided by 2, just to give us a 1 in that first column. So row 3 divided by 2, 1, 0, 2, 0. Now the first thing you notice here is that I actually have in my new row 1 and my new row 3, I've got the same row, so I can actually cancel those two out. And again, that's what we expect to see when we have eigenvectors. So we expect at least one row to cancel out. So I'm going to leave row 1 as it is. It stays the same, so 1, 0, 2. Let's divide row 2 by 2. That gives me 0, 1, minus 2, 0. Line these up a little bit better. And let's subtract row 1 minus row 3. So that gives rid of my bottom row. So let's write these now as equations. I've got, if my vector v is equals to v1, v2, v3, then my first row is going to give me the equation v1 plus 0 times v2 plus 2v3 is equals to 0. My second row is going to give me v2, this expression here, minus 2v3 is equal to 0. And my third row was just zeros equals to 0. So I have two equations for two unknowns, which means I'm going to have an extra unknown. So I'm free to choose whatever I want for that unknown. So let's take v3 equals to, let's say, t, some real number, any real number we like. Then that second equation there tells me that v2 is equals to 2 times v3, which is equal to 2t. And that first equation tells me that v1 is going to be minus 2v3, which is equal to minus 2t. So my vector v, for the case of lambda is equal to 0, is going to be equals to minus 2t, 2t, and t. Or, because I can define an eigenvector up to any multiple, I can set that equals to minus 2, 2, 1. I can choose whatever value of t I want. Now I'll let you try and solve for the eigenvectors of lambda is equals to 3 and lambda is equal to 6. I'll give you the solutions. For lambda equals to 3, the eigenvector is -1, -2, 2. And for lambda is equal to 6, the eigenvector is equal to 2, 1, 2. And I showed that explicitly in the solution set. Okay, so now we have all of the eigenvalues and eigenvectors. What are we going to do with that? So let's look again at question 1. So we have the eigenvalues and eigenvectors. In the next part, we're asked to find an orthogonal matrix P that diagonalizes my matrix A. And we remember that the way we do that is by forming the matrix of eigenvectors. So this is part B. We're looking for the matrix P inverse A P. What is the matrix P that diagonalizes A? And what is the matrix D? Well, the thing to remember here is that if I choose my matrix P to be the matrix of eigenvectors, that is, writing down the eigenvector for lambda is equal to 0 was -2, 2, 1. Eigenvector for lambda equals to 3 was -1, -2, 2. And the eigenvector for lambda equals to 6 was 2, 1, 2. So those are my eigenvectors. So these are, let me write down which ones these are. This is eigenvector for lambda equals to 0. This is eigenvector for lambda equals to 3. And this is the eigenvector for lambda equals to 6. The thing to remember is that if I pick my eigenvectors to be in this order, then my diagonal matrix of eigenvalues has to match that order. So D will have to be 0, 3, 6. A diagonal matrix of eigenvalues 0, 3, 6. So that's our matrix D. Okay, so let's take a look at part C. Now we're going to actually apply the results from parts A and B to solve a system of differential equations. So in this case here, we're told dx dt, dy dt, dz dt, they form some system here. First thing to do is to notice that this actually does form a differential equation involving my matrix A. And then we're going to solve that using the initial conditions that were given there. So let's take a look at that. This is part C. So the first thing again to notice is that I can write x dash y dash z dash, and by that of course I just mean time derivatives of x, y, and z, is equals to, writing this all as a matrix, is going to be 3, 2, 2, 2, 2, 0, 2, 0, 4 times x, y, z. So in other words, writing this as a matrix equation, we've got the derivative of the vector x is equal to matrix A times vector x. So this system of differential equations has been written as a matrix equation, and I can immediately write down the solution. X of t is equal to C1 times the first eigenvector, 2, 2, 1, times e to the first eigenvalue times t, plus C2 times the second eigenvector, -1, -2, 2, times e to the second eigenvalue times t, plus C3, third eigenvector, e to the third eigenvalue times t. And again, the thing to remember here is that I've matched the eigenvalues and the eigenvectors. So this is the eigenvector corresponding to lambda is equal to 0. This is the eigenvector corresponding to lambda is equal to 3. And this is the eigenvector corresponding to lambda is equal to 6. So I can write that out in terms of single columns. So I'm going to get, this is the vector x, so I get x of t, y of t, z of t will be equals to minus 2c1 e to the 0 t, so e to the 0 is just 1, minus 1 times c2 e to the 3t, plus 2 times c3 e to the 6t, and so on for the other rows. 2 times c1 minus 2 times c2 e to the 3t, plus c3 e to the 6t. So you notice that I'm just reading off each row here. Last row we have c1 plus 2c2 e to the 3t plus 2c3 e to the 6t. And that's our solution in terms of those coefficients c1, c2, and c3. To fix those, we're going to need to use the information at t is equal to 0. So at t is equal to 0, we're told that x is equal to 0, y is equal to 0, and z is equals to 1. So let's substitute that into the expression that we've just found. So when t is equal to 0, I get x equal to 0, y equal to 0, z equals to 1. I'm going to have minus 2 times c1 minus, when t is equal to 0, e to the 3t is 1, so I get minus c2 plus 2c3, 2c1 minus 2c2 plus c3, c1 plus 2c2 plus 2c3. And you notice here that this is actually now a system of linear equations. So I can write this as a matrix: minus 2, minus 1, 2, 2, minus 2, 1, 1, 2, 2, multiplied by C1, C2, C3. Okay, so I've written that now as a system of linear equations to solve, and we can use that. We can do that using our methods from first year. So let's see what that looks like. So here's the system I want to solve. Minus 2, minus 1, 2, 2, minus 2, 1, 1, 2, 2, 0, 0, 1. So I let you solve those. I'll give you the solution. Or why don't we work through it anyway? We might as well. So we've got R1, R2, and R3. So let's see what we can do here. Let's move R3 up to the top. I like R3. He's got a 1 in front, so that's nice. So 1, 2, 2, and a 1. Let's add together R1 and R2 to get rid of that first column. So I've got 0, minus 3, 3, 0. And we need something else. Let's put down let's just put down R2 again, because we're going to have to get rid of. Why don't we add together R2 and minus 2 times R3. So we're going to have R2 minus 2 times R3. That's going to give me 0 in the first column. That's what I want. R2 minus 2 times R3. That's going to give me minus 2 minus 4. So that's going to give me minus 6. And I've got R2 minus 2 times that, which is going to be 1 minus 4, so that'll be minus 3. And again, I've got R2 minus 2 times R3, which is going to be minus 2 here. Okay, so let's keep R3 right where it is. I like that top row. I'm not going to move it, so that's now called R1. 1, 2, 2, 1. Let's divide my second row by minus 3. And let's take my third row and add together third row minus 2 times second row. So I've got third row minus 2 times second row. I get 0. I get minus 6 minus 2 times minus 3, which will be minus 6 plus 6 is 0. Minus 3 minus 2 times minus 3, so that's minus 3 minus 6, which is minus 9. And I've got minus 2, that's a minus 2 there. Minus 2 times 0, so that stays minus 2. And we have this now in reduced row echelon form. So I can write this as my top equation is going to be C1 minus 2C2 plus 2C3 is equals to 1. I've got C1 minus, sorry, that's it. C2 minus C3 is equal to 0, and I've got minus 9C3 is equal to minus 2, and now I can solve by back substitution. So C3 is equals to minus 2 divided by minus 9, so 2/9. C2 is equals to C3. And I have that C1 is equals to 2C2 minus 2C3. So that's going to be equals to, let's take care here now. So that should be equals to 0. Okay. All right, so that's our solution to question 1, part A, B, and C. So now we're going to take a look at part D. So part D takes a sort of left-hand turn here. It says, let's say we have a quadric surface here. We're given the quadric surface. We want to write this in terms of its principal axes and find an orthogonal matrix that diagonalizes this. And then we want to find out what shape this quadric surface is. So the first thing we need to do is to rewrite this in the form X transpose AX is equals to the same right-hand side, 24, and figure out what A is. So the way we did that was by identifying the diagonal terms as corresponding to x squared, y squared, and z squared. So that's 3, 2, 4, x squared, y squared, z squared. And then the off-diagonal terms are taken care of by the remaining mixed terms. So I've got 4xy, I split that in two, so I get 2xy and 2xy. And those go into the xy and the yx components of my matrix. I've got 4xz, so I'm going to again split that up into 2xz and 2xz. So I have two coefficients, 2 and 2. And I put those into the xz and zx components of my matrix. And finally, there's no term yz, so there's not going to be a component in yz. And so you notice here that this matrix is in fact exactly the same matrix as we started off with. It was A. So I don't need to solve the eigenvalues and eigenvectors. I already did that in part A. And I can use that now to immediately write down the matrix P that diagonalizes this thing. And write down its simple form, its form in terms of its principal axes. So the matrix P is the matrix of eigenvectors. We've actually already done that. So the matrix of eigenvectors was -2, -1, 2, 2, -2, 1. Oop, I got that right. Let's try that again. Matrix of eigenvectors was -2, 2, 1. -1, -2, 2, and 2, 1, 2. And the diagonal was 0, 3, 6 along the diagonals. Okay, so now we're ready to write down the form of my quadric surface here, my quadratic surface, by writing down in terms of new coordinates x squared, big y squared, and big z squared. And the coefficients multiplying those things are exactly my eigenvalues. And what appears on the right-hand side is the same right-hand side as we've always had. It's equals to 24. That doesn't change by a coordinate transformation. So you see that I get a 0 x squared, so this expression does not depend upon x. It does depend upon y and z, and so what we're going to do here is divide by that 24. So I get 3y squared over 24 plus 6z squared over 24 is equals to 1. Let's do some cancellation here. 3 on top, 8 left on below, 6 on top, I get 4 left below. So I get the equation y squared over 8 plus z squared over 4 is equals to 1. So what shape does this represent? Well, it's going to have no x dependence, which means it's true for all big X, which means this thing extends infinitely in the x direction. It's also in the YZ plane got what looks like an elliptical cross-section. That is, I've got y squared over 8 plus z squared over 4. You notice that both of the signs of those are positive. It's going to intersect the y-axis at plus or minus the square root of 8, and the z-axis at plus or minus the square root of 4. So this thing is going to be a cylinder with an elliptical cross-section. Let's see if I can draw that. So here is big X, Y, Z. Those are the new coordinates. Let me just make that a little clearer. Big Y. And this thing has an elliptical cross-section in the XZ plane, which means that it looks something like this. And it's extended infinitely in, it's an elliptical cross-section in the YZ plane. So let me just label my axes there. Let's call that X. And let's call this one Y. Okay, the last part of this question asks us to prove something about symmetric matrices. This is part E. We're told that A is a symmetric matrix. Which implies that A transpose is equal to A. We're told that P is orthogonal. Which means that the transpose of P is equal to P inverse. And we're asked to prove that P inverse AP is symmetric. So I want to prove that the transpose of that thing is itself. So P inverse AP is symmetric. So let's take the transpose of this and try and show that indeed it is the same thing. So first thing we notice is that I can replace P inverse with P transpose because P is orthogonal. Now I've got the transpose of the product of three matrices. That's going to give me the transpose of those matrices multiplied by together and reversed in order. Finally, we notice that we've got P transpose is equal to P inverse. A is symmetric, so A transpose is A. And I've got P transpose, which is equals to P. So you see that I got P inverse A P transpose is itself, which implies that P inverse AP is equal to a symmetric matrix. Okay, I'm going to jump now to the last question, question 4, to try and get a little bit more practice doing problems involving quadric surfaces. So in this problem, we're going to be given a quadric surface again, and we need to basically express this quadric surface in its simplest form. So we're going to find eigenvalues and eigenvectors. But you see there's going to be a couple of new wrinkles to this question. So this is looking at question 4. Okay. So question 4. So we are given the quadric surface x squared plus y squared minus plus 3z squared plus 4xz plus 4yz is equals to 5. And we want to express that in terms of a matrix equation. So what I mean by that is an equation V or X transpose AX equals to 5. Actually, in the question it uses V, so let's stick with that. All right, so here my matrix, my vector V is equals to x, y, z. So let's write down what A is. We've seen how to do this in the last question. We take the diagonals to be the x squared, y squared, and z squared terms. We take the off diagonals to be the corresponding mixed terms divided by 2. So I've got 4xz. That corresponds to 2 in the xz and 2 in the zx components. I've got 4yz, so that corresponds to 2 in the yz and 2 in the zy. And there's no xy component, so there's 0, 0 in the xy and yx elements of my matrix. So this is my matrix A. The next thing we need to do is to show that we have eigenvalues and eigenvectors of this matrix. So we're actually first of all asked to show that lambda is equals to 1 is an eigenvalue. So there's a couple of different ways to show that. The way I'm going to do it is by calculating the characteristic equation for A, that is, calculate the determinant of A minus lambda I vector. Set that equals to 0 to get my characteristic equation, that is a cubic equation for lambda, and then substitute in lambda is equal to 1, or lambda minus 1. Lambda is equal to 1, and show that that is equal to 0. So let's try that. We got lambda subtracted from the diagonal. This is my determinant to calculate. So we've already seen how to do this. I'm going to do it a little bit quicker now. 1 minus lambda, 3 minus lambda, minus 4, minus 0 times stuff, plus 2 times 0 times 2, minus 2, 1 minus lambda. So I've got, again, let's not just jump in here and multiply it all out. 1 minus lambda, let's multiply out the things in the square brackets at least. So I've got 3 minus 3 lambda minus lambda, so minus 4 lambda. I've got plus lambda squared, minus 4. Minus 4 times 1 minus lambda. And in fact, we already spot right away that there's this common factor of 1 minus lambda. So we have lambda squared minus 4 lambda, and I'm going to have 3 minus 4 minus 4, so I'll have 3 minus 8 is minus 5. We're factorizing that. Lambda minus 5, lambda plus 1. And that's equals to 0, which gives me my eigenvalues. Now let's say I hadn't spotted that factorization. Let's say I was at this point in the calculation and I didn't notice that lambda minus 1 was going to be a factor. So let's say I just plowed ahead and multiplied all this out. How would I figure out that lambda minus 1 was equal to a factor of that? And how would I figure out what the other two solutions were as well? So let's see how you do that. So let's come from this expression here and jump down here. So let's go ahead and multiply all this out. So I've got 1 minus lambda lambda squared minus 4 lambda minus 1 minus 4 plus 4 lambda is equals to lambda squared minus 4 lambda minus 1 minus lambda cubed plus 4 lambda squared plus lambda minus 4 plus 4 lambda. So let's gather together my terms here. I've got minus lambda cubed. I've got lambda squared and a 4 lambda squared, so I'm going to have plus 5 lambda squared. I've got minus 4 lambda plus lambda plus 4 lambda, so that will give me plus lambda. And I've got minus 1 and minus 4, so that'll give me minus 5. So that's my cubic equation, and that's got to be equals to 0. So how am I going to prove that lambda is equals to 1 is a root? Well, what I'm going to do is I'm going to substitute in lambda is equal to 1. So minus 1 cubed plus 5 times 1 squared plus 1 minus 5 is equals to minus 1 plus 5 plus 1 minus 5, which is indeed equals to 0. So that implies that lambda equals to 1 is a solution. That is, lambda equals to 1 is a root, is an eigenvalue. So now I've got one eigenvalue. How do I figure out how to factorize and find the other eigenvalues? Well, the way I'm going to do it is by long division. So let's write out my cubic equation here again. Minus lambda cubed plus 5 lambda squared plus lambda minus 5. And I know that 1 minus lambda is a root or a factor of that expression. It's a factor of that expression because lambda is equal to 1 is a solution. I'm going to actually write this not as 1 minus lambda, but as lambda minus 1. Keep that lambda in front. I'm just going to divide it in to find out what the remainder is. So you can see that I need to multiply this expression by minus lambda squared. When I do that, I get minus lambda squared plus lambda, minus lambda cubed plus lambda squared. Subtract those two terms. You see that that's going to cancel. And we're left with 5 lambda squared minus lambda squared is 4 lambda squared. Let's bring down the next term. I need to divide 4 lambda squared minus lambda by lambda minus 1. I'm going to do that by multiplying by 4 lambda. That gives me 4 lambda times lambda minus 1 is 4 lambda squared minus 4 lambda. Again, let's subtract that. So those are going to cancel. I get lambda plus 4 lambda, which gives me 5 lambda. Let's take down the next root. Next term, which is minus 5. And to divide lambda minus 1 into 5 minus lambda 5, I'm going to multiply by 5. Once again, I subtract those two pieces. This cancels and this cancels, and I'm left with 0. So this is an exact factor. It divides exactly in, there's no remainder, which means that my cubic equation can be written as lambda minus 1 multiplied by minus lambda squared plus 4 lambda plus 5 is equal to 0. I can factorize the quadratic there, minus lambda, lambda. I've got 5 and 1 equals to 0. So that gives me exactly the same eigenvalues as before. Lambda is equals to 1, lambda equals to 5, or lambda is equal to minus 1. Okay, let's move to the next part of the problem. We found the eigenvalues. Let's look at part C. So in part C, we're asked to write down the quadric surface in terms of the principal axes big X, big Y, and big Z. And we remember that we can do that without bothering to figure out what the eigenvectors are, as long as we know what the eigenvalues are. Is equal to the same right-hand side, which was 5. So all I need to do is to substitute in those eigenvalues. I've got 1 times x squared plus 5 times y squared minus 1 times z squared is equals to 5. So this is the surface that I'm trying to describe. We notice that there is a minus sign in front of the z squared, which means that there's not going to be a solution on the z-axis. So I can try and sketch what this thing would look like. Let's divide by 5, just to make life easy. So I get x squared divided by 5 plus y squared minus z squared divided by 5 is equals to 1. And we can immediately read off that there's going to be points x is equal to plus or minus root 5, y is equal to 0, z is equal to 0, x is equal to 0, y is equal to plus or minus 1, z is equal to 0, and no solutions on the z-axis. That is when x and y are both equals to 0. So this thing doesn't touch the z-axis. Let's sketch what it would look like. Here's my z-axis, my big y-axis, my big x-axis. Here's y. Here's x. I know that this thing doesn't touch the big x-axis, but it does touch the x and y axes, and it crosses the points x is equal to plus or minus 1, plus or minus root 5, excuse me, and y is equal to plus or minus 1. So this is plus root 5, plus 1, minus 1, minus root 5. And then this shape is going to be a hyperboloid of one sheet. Now, in the next part of the problem, we're asked to calculate the orthogonal matrix P that transforms from my old coordinates to my new coordinates. Now, to do that, I'm going to calculate the eigenvectors. So, again, I will just give you those eigenvectors. I'll leave it to you to calculate, to show that they are indeed those values. So for the eigenvalue lambda is equals to minus 1, the eigenvector is going to be 1, 1, minus 1, and I will normalize that, that is, make sure that it has unit magnitude, by dividing by the square root of 3. For the eigenvalue lambda is equals to plus 1, I've got v is equals to minus 1, 1, 0, and again I'm going to divide that by its magnitude, so it has magnitude 1. And for lambda is equals to 5, I've got v is equals to 1, 1, 2, dividing by its magnitude to make it a unit vector. Now we're going to write down the matrix P that transforms from my old coordinates to my new coordinates, big X, big Y, big Z. And to do so, I'm going to actually have to remember which of my coordinates corresponded to which eigenvalue. So when I wrote down my eigenvalues, lambda 1, x squared, lambda 2, y squared, lambda 3, z squared, you can see that I associated x squared with the eigenvalue plus 1, y squared with the eigenvalue 5, and z squared with the eigenvalue minus 1. So I have to be respectful of that when I'm writing down what p is. So x corresponded to lambda is equals to 1, y corresponded to lambda is equals to 5, and z corresponded to lambda is equal to minus 1, which means that I have to put the eigenvectors in P in the same order. So the eigenvectors in P are going to correspond to lambda is equals to 1. So that was given by 1 divided by root 3, 1 divided by root 3, minus 1 divided by root 3. Eigenvector corresponding to lambda is equals to 5, so that was 1 divided by root 6, 1 divided by root 6, and 2 divided by root 6. And the eigenvector corresponding to eigenvalue minus 1. Oh, I got those backwards. So this is the eigenvector corresponding to lambda is equal to minus 1. Put that over there. It's much easier to do on my little screen here than it is for you in your notes. And I've got eigenvalue lambda is equal to plus 1 with eigenvector 1 over root 2 minus 1 over root 2, 0. So again, this is lambda equals to 1. This is lambda equals to 5. And this is lambda equals to minus 1. And you notice that I've matched the ordering there. So this is my relationship. The last thing that we're asked to do is to calculate the points of intersection of the quadric surface with its principal axes in terms of the little x, little y, little z coordinates. So let's go back and take a look at our picture here. What were the points of intersection of the surface with its principal axes? Well, you can see that those are occurring here, 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 and here. So what are those coordinates in our big X, Y, Z coordinate system? So let's use a different color. This point here corresponds to when big Y is equal to plus 1. So that's 0, 1, 0. This point here corresponds to when big X is equal to minus root 5. So we get minus root 5, 0, 0. This point here is going to correspond to when y is equal to minus 1, x is equal to 0, and z is equal to 0. And this point here corresponds to the point root 5, 0, 0. So those are the 4 points in big X, big Y, big Z coordinates that we need to search for. So we have the points plus or minus root 5, 0, 0, or 0 plus or minus 1, 0. And that's in X, big Y, big Z coordinates. So how do we express that in little x, little y, little z coordinates? Well, the way that we're going to do that is by using the expression that we just found here. Little x, little y, little z is going to be p times the coordinates x, y, z, big X, Y, Z. So for plus or minus root 5, 0, 0, we've got that little x, little y, little z is equals to p times big X, big Y, big Z, and we just found that, let's keep p right there, p was 1 over root 2 minus 1 over root 2, 0, 1 over root 6, 1 over root 6, 2 over root 6, and 1 over root 3, 1 over root 3, minus 1 over root 3. And we're going to multiply that by root 5, 0, 0. That's the coordinates of the point root 5, 0, 0 in big X, big Y coordinates. If I wanted to find the coordinates for minus 5, root 5, 0, 0, I'd put in minus 5, 0, 0 here. If I wanted the x, little y, little z coordinates for 0, 1, 0, I'd put that in here, and so on. And so that's how I find the coordinates in my original coordinate system, little x, little y, little z, of my crossing points, my intersection points.